7.4 is going to be specific to integrating rational functions. So remember what a rational function is: a function of the type p of x over q of x, where p and q are both polynomial. And I'll give you this definition more formally, okay? So just to kind of put it, where do we insert this into our sort of tool belt of now integration techniques? We always kind of have a hierarchy where it's like, okay, can I look at it and I just know what the antiderivative is? No. Can I simplify it algebraically and then I'll know the antiderivative? No. Can I make a u sub? No. Can I do integration by parts? No. Is there a radical? Then maybe trig substitution. Okay, and then this one would be kind of adjacent to that. Is it rational? Then maybe I can use partial fraction decomposition and integrate it that way. All right, so what is partial fraction decomposition? So here's the general idea. You don't need to, please don't write this down. These slides are available to you. You can write down this little example if you want, because I think this helps explain the idea. We're used to taking a situation like this and combining like terms, or sorry, not combining like terms, coming up with a common denominator, right? In this case, the least common denominator, would be x minus 1 times x plus 2, right? And then you would multiply both denominators by whichever factor is missing. So I would have to multiply this one by x plus 2, and I would have to do that to the numerator as well. And I would have to multiply this one by x minus 1, and I would do that to the numerator as well. And now I can combine them into a single fraction with the same common denominator. I can multiply everything out, and I can get here, right? You guys have been doing that since at least Algebra 2. So, partial fraction decomposition is going the opposite direction. We're going to be starting here, and what we're going to want to do is decompose it into this situation, which is what we call partial fractions. Right? And so the idea there is it would be much, much easier for you to integrate, like if we had an integral that involved this expression, it's much easier to integrate these than it is to integrate this. Does that make sense? Because these you can just do a simple u sub for, and you're going to end up with like natural log of what's in the absolute value of what's in the denominator. All right, so that's the general idea. So first we have to figure out, okay, how do we start with kind of a complex rational expression and decompose it into much simpler partial fractions, because it's a little bit harder than going the opposite direction, than coming up with a common denominator, multiplying by missing factors, and then expanding, okay? All right. So, a lot of information on this page. I'll give you some that I think you should write down. So I already told you that a rational expression is a function of the form p over q, where p is polynomial and q is polynomial. That's important. Remember what a polynomial is? Expression involving a variable with only whole number powers. So it can't be like x to the 1/2 or x to the pi or anything like that. It's only whole number powers. All right. The other thing is, remember the degree of the polynomial is the highest power on your variable, right? if you have a rational expression where the degree of P is greater than the degree of Q, what you have is an improper rational expression, meaning it could be simplified into basically a mixed rational expression, the same way you would simplify an improper fraction into a mixed number, right? If I had like 27 over 4, I could go, okay, how many times does 4 go into 27? 6. What's remaining? 3/4, right? So it's 6 3/4. Does that make sense? We call this an improper fraction because the numerator is larger than the denominator. And then I can create a mixed number, basically, by doing division, right? Same idea with polynomials. If you have an improper polynomial, you can use polynomial long division and rewrite it as your quotient plus your remainder over your divisor. So that's the first thing. So let's do an example with that. Let's say we want to integrate x cubed plus x over x minus 1. The first thing you want to check for is this a proper or improper rational expression? Well, the degree of the numerator is 3, the degree of the denominator is 1, so it's improper. So we should be able to use polynomial long division and simplify this. So it might have been a while, but that's okay. Polynomial long division is none too hard. So here's how I suggest doing that. We're going to set up your dividend goes under the division symbol. And I like to always write it in decreasing order of degree. And if it skips degrees, I put a placeholder there. So this goes from x cubed, which is third degree, to x, which is first degree. So what I'm going to do is go plus 0x squared, and then I'll do plus x, and then I'll do plus 0. And that'll just create nice, neat columns. And you'll always have the things that you need, the like terms that you need. All right, and then my divisor goes out front. Okay. When you do this division, you do it just like you do regular long division, which I'm sure you all remember from 4th grade. Just kidding. It's been a while, so I don't blame you if you don't. But here's how you do it. You focus on only the lead term of the divisor. I want you to tell me, what do I need to multiply that lead term by to get me this term in my dividend? So what do I need to multiply x by to get x cubed?
X.
X squared. So I'm going to put that here just to keep things organized. I like to keep them all in the same degree columns. All right. And then what you would do in long division is you would take that part of the quotient and you would multiply it back by the divisor. Okay, so I'm going to multiply x squared by x minus 1. And that's going to get me x squared times x is x cubed. X squared times negative 1 is negative x squared. And then we subtract. But remember, we're subtracting that whole thing. X cubed minus x cubed is 0. Good, that's what we're trying to do, is progress through this. And then we have 0x squared minus negative x squared, which is going to be positive x squared, right? And if you'd like, you can bring down that next term, so plus x. And now we start the process over again. So now I start the process over again where I'm just focused on this lead term and I'm trying to think, what do I need to multiply x by to get this term? So to get x squared. And that is, of course, just x, right? And then I do the process over again. I'm going to take that x and multiply it by my divisor. So x times x is x squared. X times -1 is negative x. And I subtract. Make sure you put parentheses around this so that you remember to subtract both terms. You end up with 0. X minus negative x is 2x, right? You can bring down the plus 0 if you like. All right. So again, we're focused on my lead term in the divisor. What do I need to multiply x by to get 2x?
2.
Positive 2, so plus 2. Take that piece of the quotient, multiply it back by the divisor. We get 2x minus 2, subtract. We get 2. And that's a remainder. How do I know that's a remainder?
Because x doesn't go into.
There's nothing, yeah, x doesn't go into 2. There's nothing I can multiply x by that'll give me 2, right? There's no polynomial term I can multiply x by to get me 2. All right. So, what does that mean? That means that this becomes the integral of what we just came up with is an equivalent expression for that improper rational function. And that expression is just the quotient, which is x squared plus x plus 2, plus the remainder divided by the divisor. X minus 1, not x minus 2. Oh. And so if you forget, if you get lost in this, you can do, I like to just do like a basic, long division problem. All right, what if I had 46 divided by 3? Well, I would write it like 3 goes into 46, and we would go, okay, 3 goes into 4 once. Right? And then where do we go from there? You multiply 1 by 3, I get 3. You bring down the 6. I'm sorry, you subtract minus 1, you bring down the 6. Then you go, okay, 3 goes into 16 5 times, right? 3 times 5 is 15, subtract. That's my remainder. So what's the mixed number version then? 46 over 3 is 15 plus remainder over divisor. So it's 15 and a third, right? So sometimes if I forget kind of where I'm at in a polynomial long division problem, it just helps to look at a simple regular long division problem because all the processes are the exact same. So if you forget, like, okay, I've done the long division now, I can't remember what to put the remainder over, that might help. All right, but now we have a new integral that's going to be a lot nicer to deal with. We can just do term by term anti-differentiation here, right? So Antiderivative of x squared is x cubed over 3 plus x squared over 2 plus 2x. Now what about this integral? I can pull the 2 out. The integral of 1 over x minus 1 dx. All right, so technically you need a u sub, but this is going to be one of those situations just like when we learned how to integrate like sine and cosine when there's a multiplier on the angle quickly without having to make the u sub every time. You can kind of do that here. Let's make the u sub one time. So here I would let u equal x minus 1. Then du is just dx, right? So I have 2 times 1 over u du. What's the antiderivative of 1 over u? Anybody chat? Antiderivative of 1 over u? The derivative of what would give you 1 over u?
The natural log of u.
Natural log. But remember, when you go the opposite direction, you have to do absolute value. So it's natural log absolute value u. So it's 2 natural log absolute value of x minus 1. So here's what I'll say. When you have a constant, when you're trying to integrate a situation like this that's just a constant over x plus or minus another constant, it's just going to be that constant times natural log absolute value of whatever the denominator is. The only time you'll run into an issue is if you have a multiplier on your x. So if this was like 3x minus 1 or something other than just x minus 1, then you would want to do a proper u sub because that's going to affect what du is. That's going to give you like a different fractional coefficient, if that makes sense. But as long as it's just a constant over x minus 1 over x plus 1, that antiderivative is always going to come out similar to this. All right, so my final answer, x cubed over 3 plus x squared over 2 plus 2x plus 2 natural log absolute value x minus 1 plus c. All right, questions about that one? All right. So always the first thing you want to check for, you see it's a rational function that you're trying to integrate. First check, is it proper or improper? So either unmute yourself or tell me in the chat, is this a proper rational expression or an improper rational expression?
Proper.
It's proper. So we don't need to do any long division. So the next thing to do is factor, which it's also probably been a while for. That's okay, we can get a crash course here. So I'm going to take that I'm just going to look at the integrand for now. We're not going to do calculus for a while. So I have x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. So I want to factor this out. Do you guys remember how to factor trinomials like the one in the numerator? So the one in the numerator just has x squared as its first term, so that means it's going to be x times x And right, what we want to think about is we need two numbers that multiply to make -1 and add to 2. Whoops. You know, I just realized we don't need to worry about the numerator. You don't have to factor the numerator. We just have to factor the denominator. Apologies. Leave the numerator alone. It doesn't factor anyway. All right, x squared plus 2x minus 1. The denominator, first of all, I can factor out an x, right? And then I have 2x squared plus 3x minus 2. Now, do you remember how to factor these types of trinomials? It's a little harder when the coefficient is something other than 1.
Don't you multiply like the first and the last?
Yeah, so I have a way that I like to do it. Some students learn various ways. You usually learn this in like Algebra 2. I'll tell you how I like to do it. I like to go like this. I'll start out and I'll put my leading coefficient with my leading variable in both sets of parentheses. Now, is that going to work in the end? No, because that would make 4x squared, right? So what I'm going to have to do, I'm going to end up dividing out the extra factor at some point. So don't worry about that. Now we're going to do what Claire said. You multiply the leading term, the leading coefficient times the constant, and that's the number you want to multiply to. We want to multiply to make -4. We want to add to make the linear coefficient, which is 3. So I want to add to 3. So what two numbers will multiply to make -4, but when you add them give you +3? Answer my riddle. You multiply them together, they make -4. You add them together, they make +3.
-1 and 4.
-1 and +4. So then I'm going to put -1 in one set of parentheses, +4 in the other. Now here's where we get rid of that extra factor that I included. You look at each set of parentheses and you divide out whatever the greatest common factor is. Here it's just 1. Here I can divide out at 2, right? And that'll leave you with the proper factored form. 2x minus 1 times x plus 2. All right, so here's what we got. We now have x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2. Now we're ready to decompose. Note what we have here. 1, 2, 3 unique or distinct is the word that they use. Linear factors. Right? So what that last slide says is that that should be able to decompose into 3 partial fractions, one with each unique linear factor as a denominator. So I'm going to put a1, which is a constant, over x, plus a2 over 2x minus 1, plus a3 over x plus 2. That makes sense, right? So they should be able to decompose into that, because if we were trying to combine these, we would need a common denominator. That common denominator would be that right there, right? And so now our goal is just going to be to solve for what A1, A2, and A3 are. So this is where we're going to get a little bit tricky. All right. So if you go way back to the days when you were actually solving rational equations like this, the way you solve a rational equation is to make it not rational anymore. And the way you make it not rational is to multiply everything in the equation by that common denominator. So I'm going to multiply both sides of this equation by x times 2x minus 1 times x plus 2. So everything's getting multiplied by that common denominator. So on the left side, all that's going to do is cancel out the denominator like that, right? And it's just going to leave me with x squared plus 2x minus 1. On the right side, it is going to eliminate all the denominators, but it's also going to leave some baggage with each term, right? So when I take this and I multiply it over to that A1 term, the x's will divide out, but I'll be left with A1 times 2x minus 1 times x plus 2, right? Likewise, when I multiply that common denominator over to the A2 term, the 2x minus 1 factors will cancel each other out, but I'll be left with A2 times x plus 2. And then lastly, when I multiply it all the way over to the A3 term, the x plus 2 factors will cancel out, but I'll be left with A3 times x times 2x minus 1. All right. Expand the right-hand side. Yes, it's obnoxious. I understand. I gave you fair warning about this unit. Lots of algebra. So I'm going to have, what, 2x squared. That's going to be plus 4x minus x, so plus 3x minus 2. It's going to be x squared plus 2x. Going to be 2x squared minus x. One more expansion. We're going to distribute all the A1, A2, and A3. All right, so distributing A1, I get 2A1 x squared plus 3A1x minus 2A1. Distribute to A2, I get plus A2 x squared plus 2A2x. I get plus 2A3 x squared minus A3x. Okay? Make a little note right here. Now we're going to group like terms. So based on their x, the x part of each term. So I want you to group all the x squareds together. So we're just moving things around on the right-hand side. So I'll start with the x squared terms. So I have 2a1 x squared. This can be a lot to keep track of. what else do I have? I have a2x squared. So I'm going to do plus a2x squared. And then I also have 2a3x squared. So plus 2a3x squared. I'm just going to put those in parentheses just so I know that they're grouped there. All right, next let's do the x terms. So I have plus 3a1x plus 2a2x and then minus a3x. I'm just going to group those two just for the sake of recognizing that they're together. And the only thing I have left, which would represent a constant, is the minus 2a1. So I have minus 2a1, right? And that's still equal to what we had on the left-hand side, which is x squared plus 2x minus 1. All right, the next thing I want you to recognize is that all those sets of parentheses have something in common. What's the common factor in the first set of parentheses?
X squared.
So I can factor x squared out. So I'm going to do that. I'm going to actually factor it to the back. I know we normally factor things to the front, but for a specific reason, I'm going to put it on the back end of this set of parentheses. Right? So what's common to the next set? X. And the last one, remember, is just a constant. All right. So what I want you to recognize, remember that A1, A2, and A3 are constant, right? So each one of these is really just a coefficient on a variable. That's a coefficient on x squared. This is a coefficient on x. This is a constant. Well, notice that that's equal to a trinomial on the other side, on the left-hand side, which also has x squared, x, and a constant. If those things are equal, then their coefficients must also be equal. Do we agree with that? So the coefficient then I underlined in red has to be the same as the x squared coefficient, which is technically 1, right? So that gives me this equation. 2a1 plus a2 plus 2a3 has to equal 1. Same has to be true with the x terms. My x coefficient on the right has to equal my x coefficient on the left. So that gives me another equation, which is 3a1 plus 2a2 minus a3 has to equal the x coefficient on the left-hand side, which is 2. And last but not least, my constant, negative 2a1, has to equal my constant, negative 1. So negative 2a1 equals negative 1. All right, sticking around with the algebra 2 stuff. What we have here is a system of equations with how many unknowns? 3. And there's 3 equations. As long as you have the same number of equations as you have unknowns, the fundamental theorem of algebra says you will be able to find a solution or no solution. But you won't be left without an answer. So we got to review how to solve systems of equations. This one's not too bad because of the last equation. The first thing we can immediately do is solve for a1, right? So by this last equation, we know that a1 has to equal positive 1/2, right? And so once we know what a1 is, we can then create a new system of equations where we just replace a1 with 1/2. So plugging that into the top one, that would give me 1 plus a2 plus 2a3 equals 1. And then in the bottom half, that would give me 3/2 plus 2a2 minus a3 equals 2. All right, so I need to clean these up a little bit. For example, the first one, I'll subtract the 1s over to the right, and I'll get a2 plus 2a2. No, plus 2a3, I'm sorry. Equals 0. The second one, I'll subtract the 3/2. I'll get 2a2 minus a3 equals 1/2. And then you can solve this however you like, substitution or elimination. This one, I think elimination is going to be the easiest. If I multiply the bottom equation, the whole thing by 2, I'll then have a2 plus 2a3 equals 0. And then I'll have 4a2 minus 2a3 equals 1. Remember, the way that you solve by elimination is you set them up so that when you add them together, one of the variables gets completely eliminated. So now when I add these, I get 5a2 equals 1, because the a3s are gone, and that tells me that a2 is a fifth. Right, so once we know a2, just take it, I'm going to plug it in. You can plug it into any of these equations, and you'll get the same thing for a3. I'm just going to plug it into the top equation. That seems the easiest to me. So that's a fifth plus 2a3 equals 0. Subtract a fifth and divide by 2. You're going to get a3 is negative 1/10. Whew. Okay. We're almost to the calculus. So remember what we did there. We solved for the constants so that now we know these constants and we can break these down into this, that the original integrand gets broken down into those specific partial fractions. So I can now rewrite my integral like this. I'll do it at the top since that's what space I have left. So it's the integral equivalently of, remember that a1 was 1/2. So that's 1/2 times, I'll just do 1 over x, plus a2 is 1/5, so 1/5 times 1 over 2x minus 1. And a3 was negative 1/10, so minus 1/10 times 1 over x plus 2 dx. Now you can for sure just think of that as 3 separate integrals. So that would be 1/2 1 over x dx plus 1/5 integral 1 over 2x plus 1 dx minus 1/10 integral 1 over x plus 2 dx. And now you can actually solve those. You know that 1 over x is, so this is going to be final answer, 1/2 natural log absolute value x plus 1/5. This is the situation where I said you should do a u sub. If you let u equal 2x plus 1, you're just going to end up having du equals 2 dx, and you're going to move the 2 over to become 1/2. So it actually does end up being the same. You're just going to end up with a coefficient of the reciprocal of whatever's in front of x. So you can verify for yourself and actually make that u sub, but it's going to end up coming out to 1/2 natural log absolute value 2x plus 1. And then this one is minus 1/10 natural log absolute value x plus 2. And then plus c. And you would want to clean that up a little bit. Rewrite the 1/5 times 1/2 as 1/10. And we can actually...
Wait,
sorry, go ahead.
Isn't it 2x minus 1?
Oh, thank you, not plus 1. You're right. I'm wrong. That's minus
So
and that's
just to
minus.
clarify the little rule thing, when you have a coefficient of x in the denominator, you just take the reciprocal of that coefficient, then natural log of the denominator?
Yes.
Okay.
And you can actually condense that answer down to a single logarithm, but I think we've had enough for today, and we can focus on that next time. Eva with an enthusiastic nod of yes.